In this presentation, I'm going to talk about the predictive tool that we call the 5-line models. It's a sets of equations that capture all the challenges that in previous models had it on calculation of areas in this SAGD environment. So first of all, we talk about Butler model because that's been used for decades now, 20 years at least. And a lot of challenges with the Butler comes because there's a misunderstanding of this model. This model is developed based on the heat transfer at the steam interface between the reservoir and the steam chamber. But SAGD in reality is a thermodynamic problem. So a lot of people asking me, where is the quality of steam that we're injecting in the Butler formula? It doesn't have a quality. And that's really because the quality change of steam doesn't change the temperature for the constant pressure. And that cannot be captured in the heat transfer model that what Butler use. And really just calculate the temperature profile inside the reservoir for the constant temperature at the boundary. And once the temperature goes higher, less viscosity means less rate, but it doesn't have any function about the thermodynamics of what's going on inside the reservoir, inside the chamber and reservoir. And one of the other things that's missing here is, like a lot of people doesn't understand, is a moving boundary condition. All right. So Butler is a conductive model that's been developed for the moving boundary problem. So that means there is a steam interface that's moved with the constant velocity. And a lot of people doesn't know that. And there are some limitations that it has to be addressed once we're using these models. Even for the part of the stages that can be used the Butler, we need some modification regarding that. One of the concerns I've been having last 10 years talking and teaching courses is a lot of people trying to use Butler formula for the ramp up stage. And I've been reviewing a lot of paper, mostly from academia, and some from operators try to provide different shapes of the SAGD steam chamber, like elliptical and like trapezoid, and trying to apply geometry to capture the ramp up stage. But there is one fundamental question and the problem that has to be issued. Ramp up is not the ablation mechanism that's been used in Butler formula. So can we use this? And so that's the solution we're going to talk about it here is, so there are two instabilities that we're going to talk about. All right. First instability is after the plateau, after we have the steam front develop, the steam chamber develop, and it start moving with the constant velocity into this chamber. Butler assumes it's a flat front. All right. So Butler only consider the conductive flow. This is the rate zone. Doesn't have any Darcy flow convective term. And for most reservoirs, we don't have much of the Darcy flow of the condensate into the bitumen. So we don't have this term very strongly. But if fingering happens, that's a game changer. All right. If it's a system works based on the fingering and you assume this is a flat front, this is a game changer. All right. So, and there is one paper that we discussed this, but let's go simple in this presentation because of the limited time we have here. Is it flat front? All right, this is a $1 million picture that every operator have to use it in front of them. All right, so this is one offset well, and we show here how the SAGD chamber is developing here. And we put line to make it clear. Other than the top zone, other than this zone that we have a gas encroachment into the reservoir, other part is pretty flat. So that means that's Butler formula for the plateau stage. Once we have a moving boundary going into the reservoir in semi-homogeneous reservoir, we do not have the fingering that being the game changer that limit us of using the Butler formula. So it's very applicable for the plateau stage using Butler formula. But is it valid for rise up or ramp up? So before going further and talking about a ramp up stage, let me explain what sort of instability we're talking about. There are three sort of instability. A steam is a gas, higher mobility, into the condensate, which has less mobility. Condensate into the hot bitumen, different phases, and hot bitumen, higher, lower viscosity into the cold bitumen, higher viscosity. And which one really matters? And in this paper that we already published, we talk about all these matters, like aspects and phases, but really the part that all the heat transfer is happening is at this front between the condensate at hot bitumen. And this is the phase that we have to consider our fingering. So now we want to talk about fingering. So we said we want to talk about condensate and hot bitumen front. So at the interface between the condensate and the hot bitumen, we have a condensate flow based on gravity, and we have the oil flow based on gravity, and these velocities are different. But there is another term that's a normal to the same phase, and that's the real player of the fingering is the condensate movement as a result of the RC flow. But condensate moving in this front at the higher mobility, because on that part, the rel perm of the water is quite high. But in here, that goes in the interface bitumen-rich part, because the rel perm of the water is dropping enormously, then the velocity is lower. So that contrast is causing this front to be fingered. All right. That's the basis of this calculation of the fingering. So I'm not going to talk about the mathematical framework of this calculation, but I'm just going to talk about the most linear stability problems is based on one disturbance or perturbation that you expose to the system. So this is the formula that you expose to the insim interface, and you have series of formulation that you have to accomplish and achieve, like a mass transfer, like how the velocity changing, or the pressure changing. At the end, you put them in sort of a matrix, and you say, if this matrix doesn't have a determinant, that means we have multiple solutions, and that's the onset of the fingering. But you have to consider like these calculations is not simple because you have imaginary terms. These are complex terms, imaginary and real terms. And then the calculation is not as simple. For someone who want to go in more detail, read these paper, and then you have but in this paper we only use the end results, and that's why I have two sort of fingering happening. One is fingering and one is vortex mixing. And anything under this red line means it happens vortex mixing. So always happens. So based on this velocity that we have at the edges, so at high temperature, it always happens. It changes by the steam interface angle, but it's if you want to talk about practical values, always happening. But the thing is, the matter is the fingering. And in this paper, it talks about the fingering, and you see that the fingering is a function of steam interface, and it talks about that this fingering happens at the onset of the fingering. So the growth of the steam chamber is controlled by that instability onset, and if you go faster, you got a huge vortex happening that you get colder front and you come up at the onset. It's a huge discussion in that paper, but the end result is at the maximum rate you come up with this equation. And previously tangent model, that is the base of the ramp up for the Butler equation, is this one. They are different, but the thing is different really we have to capture. We don't care about the geology control terms, because the problem with the the testing that we do, we come up with the core, the permeability of 2 Darcy. There is no one in the world that put exact number in the CMG or Eclipse or been using analytical models. They're fudging all those factors. But the thing normally a lot of people cannot fudge is operational controls. And this is a huge difference. This equation highly rely on the difference between oil and water and viscosity of the water, which this one really only rely on viscosity of oil only. And as you know, like in the higher temperature, the differential density between the water and oil is increasing for all the bitumens. So that means at the higher temperatures, we got more instability. So we got higher ramp up pace. Another important factor, the difference between these two is one is correlated to T, the ones we provide, and the Butler is correlated to T power of 1/3. And as you see in the field data and you be working with those, you always see that the rate is always linearly dependent to the time in the ramp up stage. And it's never follow any other type of the correlation by time. And this is the Devon Jackfish data that have been used to validate the model. Tangent always provides us very high numbers in the ramp up stage. But the issue is like a lot of people that are using this, especially the reserve consultants and operators that want to predict the future curves, they just change every parameters, and especially the Darcy in their models, like a permeability Darcy models. And so they've been using different permeability for the ramp up, for example, than the plateau. And in that stage, we are getting far from the physics. And the major comment here is if we're not providing the right parameters to get the right match for any equation or any formulation or any numerical activity, then we're doing something wrong. And so maybe we're not capturing the physics right. And that's why we cannot use the Newton's law for the small particles like a quantum physics, because that cannot be applied in that domain. And that's the same story here, that instability have to be captured in the ramp up stage, and the plateau formulation of tangerine relies on the ablation process and the moving boundary stage and the gravity drainage, which really totally different beasts that we're talking about. The other parameter that before going on and talk about final model is steam interface velocity. That's not been used widely in industry. Not a lot of people just assume there is one parameter they know, like 5 meters per year or something. But there's a method here, call it SMIT chart or the SMIT method, that really capture how the steam interface velocity is changing versus the pay zone. This equation is based on the simple moving boundary conductive flow at the front of a steam interface. But the beauty of this model is once you put in a chart, log scale dimensional temperature versus the time, and you see after sometimes you have a plateau and you see the slope. And the slope of this slope is providing us the steam interface at different locations. So we have this sort of these charts for different locations across the pay zone. So for every location, we have to plot this dimensionless versus time and calculate the UX. And then as a result, we see the UX variation along the pay zone. So to test this, there is only one unique data set, that's UTF phase B, that can be used for testing this method. Is in this field, there's different observables that located normal to the wellbore to see how the steam chamber is growing normal to the well per B2. And in this model, in this study, we want to just calculate the steam interface across the pay zone at these two ops and compare it with the response and time lag that we see between the BE1 and BGI2 and also with the Belper. That's and then compare it and see how far we are from reality. So the green and the gray are steam interface calculation across the pay zone. So this dimensionless Y is the top of the pay 1. This is the producer level. And this is how the steam interface is changing across the pay zone. And the blue is the response between the developer and the first ops. And the red is between the first ops and the second ops. There are two interesting things here that you can see. Like if you have ops wells normal to the developer, the amount of a steam interface calculated from a SMIT is kind of the same. All right, so it's not function of time. It's not function of distance. And really the response of this system provides us at any location inside the reservoir, provides us enough data to calculate the steam interface growth in that pay zone. And we see the steam interface at the top for this specific case is higher than the bottom. And for other well, we compared the steam interface across the well. This is very homogeneous reservoir. This is we're trying to put some reservoirs that can be replicated by the Butler model, the best type of homogeneous reservoirs. This is one of the old wells that have been used and one of the nicest reservoirs. And you see how the steam interface is growing. All right. So we see this as steam interface growth. But if you use a Butler formula, Butler assumptions, these are beyond the Butler formula. You have to do a lot of derivative calculation, dimensionless format to come up with this UX that assume in developing of the formula. You see in the Butler, everything goes to 0, but we see this nice shape is happening for 80% of the pay zone. So we are kind of following what Butler wants to follow in reality in most cases, at least in the homogeneous reservoir. But if you are getting further and further from homogeneous reservoir to the heterogeneous reservoir, this is not the profile we are following, all right? Especially with the mobility change across the pay zone. One of the things I should emphasize it here, the UX steam interface growth across the pay zone is highly correlated to the mobility of the water phase inside the reservoir. That is not being captured in numerical simulation by us. We're not changing relpern or water saturation that we represent that quite nicely. And in analytical, we're not doing anything really about it. But this UX interface modification really can be captured, this phenomena. And these are the factors that have been used to mimic the rates. But we see like it changes, but really they're not following the physics. So it can be any factor for me. But we, in this study, we use a tant rate. The another factor a lot of people changing to get the rates is M viscosity exponent. And it's not a matching factor. This is the PVT factor. And to trying to show M is capturing viscosity temperature dependency of the PVT of the reservoir that we're dealing with. It's a calculated parameter. And no one really does any calculation and just say, because Butler in one of these papers just mentioned like it changed between 3 to 5. So the people think they can choose any value between 3 to 5 to get the better match. But that's not the basis of this model. And another thing, like a lot of misconceptions about this is, and they don't know, is a function of temperature. Even in university, I've seen the people teaching this is a constant value and you can use it for history matching. But really, you see the M value is changing by temperature, and it's dropping as you go higher temperature because it's a viscosity trying to show the viscosity temperature dependency for that steam front. But can we use one consistent method that we use one M value and not be super wrong. This is one method, the slope method. So you're changing this dimensionless viscosity at the steam temperature to the viscosity versus T power of M. And by changing M, you get different slopes, and the slope at 1-to-1 slope is the right M. Another faster way, coded type thing is you calculate a lot of slopes for different M's, and once you hit the 1-1 line, then that's the right viscosity. And another method is we call it a log-log Butler model, and you put everything in the format of the viscosity Butler type, but in the log scale format. And by doing that, you get pretty consistent M values at the higher temperatures. But you have to reduce it by 0.35 to capture the right M value. But the best method is also still have to consider this temperature viscosity effect. But if we want to be consistent, not changing it case by case, we have to do this type of calculation. But still, we have to apply it to the right bitumen. Now we want to go to the 5-line models. That's why you see why we call it introductory level, because there are lots of misconceptions in Butler model to try to address them to get to the right stage. Then we have to go many steps. But the thing is about the Butler model, if you apply all these right factors, include the UX change, viscosity, not considered for a ramp up, only one point in life you can use Butler. And that's the end of the ramp up. So for not any of these cases, no matter how much geometry change you do, you use triangles and trapezoids and different shapes and apply a lot of mathematical gymnastics, it cannot be applied. All right. So let's assume only we can do this, but we have to have time variable factors to capture this change. And one of them is onset of the decline is only rely on thermodynamics. So it's rely based on how much overburden heat loss we got, how much heat loss we got here, and how much heat we provide into the reservoir. All right. And another factor is the coalescence factor. So how fast we get to the symmetric line. So if you get to the symmetric line, we don't have availability of this bitumen for this zone. So it has to be considered for that wellbore here. So if you apply these and just based on physics, and you see the power of decline is a function of the parameters that we've been already discussed, M, velocity of steam interface, thermodifusivity, then you get very nice physical curves that also follow the declines in these wells. So at the end, I just put a combination of these factors as a proxy model. And then now we only talk about these 5-line model as a few examples, because we only talk about 2 lines of it. Ramp up is 2 a stage. The plateau is changing as a result of rotational effect. That's not been discussed in this, but you see the heterogeneity effect. All right, the heterogeneity effect of the nicer zones versus variability. You see it in a ramp up. You see the amount of steam quality change. So if you put less steam quality, you reach the decline faster. And the steam interface profile affect your decline and also your plateau up and down. That has to be captured. At the end, the best proxy models still need to be tuning. And in this model, there are a lot of parameters that cannot be captured using the mathematics and the physics. Then the simplest way that been very popular these days to apply machine learning. So you cannot capture the fluctuation in the WOR, or ratio. You cannot capture amount of the fluctuation of the steam quality, for example. And these parameters, after we have a right proxy, can be combined with that proxy model to provide a better predictive tool. So at last, I want to thank all the operators that provide us the data and to reach this level of predictivity in this 5-line model.